What happened? Okay, sorry. So Flint's taxonomy classifies architectures of computers in four broad classes. One is single instruction, single data, which is nothing but simply our sequential computer system. Information comes from the memory to the processor. The data is loaded into the registers. Processor works on the information and returns the output back. The other one is single instruction, multiple data. When we have looked into OpenMP programs, multi-threaded program or GPU applications, those mostly work in single instruction, multiple data format. Different data, for example, if GPU is adding to vectors, different data, different location of the vectors comes into different ports of the GPU, but it essentially does the same operation. And the typical architecture in this typical computer architecture in this category is vector processor. That you take different elements of the same vector and do same operation over them in parallel. The other one is multiple instruction single data streams. That you have the same data, but different processors are working on processing different instructions. This is very popular computer architecture, HPC architecture. The fourth one is known as multiple instruction, multiple data. Different data goes to different processors, and they are free to do any operation on that, and that gives you maximum flexibility over the program. So some of the architectures, this is uniprocessor or sequential processor, vector processor or array processors, that there is one CPU which takes some data from memory and different elements of the data it sends to different coprocessors or GPU cores, and they work on that. The multiple instruction single data will not discuss. Multiple instruction, multiple data, there are two different options for that. One is known as shared memory, that you have different sections or different threads which will work differently. There is a defense group, there are thread identified by them, they will do differently, but they will do different work on different data. The other one is distributed memory. What is unique about shared memory, that whatever data is there, the entire data has the same address space. All the processor looks into the data with the same. One processor looks into a variable AI, that variable AI, the other processor writes there, the other processor will write it the same way. If we say declare a variable, that variable is uniformly seen by all the processors. And the architectures are symmetric multiprocessor, that there is a common bus which is connected to a memory and multiple processors are connected. Non-uniform memory access distributed. And in a distributed memory system, we really talk about multiple computers which are connected via a network switch. Each computer has their own address space and own instructions. Each processor has its own RAM, own. However, they are connected via network. So they can synchronize some of the work among themselves. But if one processor works on certain memory element, that is not visible to other processors because they are really destroyed. This computer and these two computers, to do something they are interacting. But if you want him to be aware of some information, you can send an information via email. So we can go via network cable from one computer to another. Shared memory, we discussed on shared memory earlier. The features are there. The general feature is that all the processors point to a common global address space. What we have discussed in OpenMP and even OpenMPI, one MPI, that multiple processors are there. One processor does any correction in the data, and that's why the cache issue is called sharing cache coherency synchronization of the issues are there. If one processor writes something, all other processor sees that this data has been changed. What changes in memory by one processor is reflected in all other processors. If they are connected to the physical same chunk of memory because they have uniform memory access, if they are at different memory locations, but virtually virtualization has been done that so that each processor sees it as a same data space, same memory space, then it is non-uniform memory access. Shared memory, multiple instruction, multiple data processes that each thread works differently on the data given, different data. But they are different data, multiple data, but your entire data sits in the same memory space. So maybe someone is operating over variable A, another is operating over variable B, another is operating over last few rows of the variable. So in that case, the threads also need some private data, which is discussed earlier. That this data, if one processor works on this data, other processor cannot see that data. So how is that created? The entire data sits in the same space. When you run an OpenMP program here, the entire data is here in this memory. So basically, the private data is tagged that you can see, you can define one variable name, but in the background there is another variable, another address space given specific to that particular processor. Cache coherence is a very important issue, and it arises in the shared memory systems. If you do not ensure cache coherence, you will get very poor performance. And you can get wrong result also on the accuracy also. It's a very programmer friendly platform. You see that you have the original code, that's what done in the PyCode. You have an original code and independent this part has to be parallelized, you write a simple construct and parallelize that. You don't need to revoke anything. Apart from cache coherence equals sharing, etc. But parallelization will be done. What you may do it wrongly, you may do it in an inefficient manner, but parallelization will be done very simply. You identify some iterations which are decoupled or independent iterations, and you write that hashtag for OMP parallel, it will be parallelized. You don't need to proximity to the memory to the CPU. So when we talk about a shared memory system, all the CPUs are sitting in the same box and attached to the same RAM via PCI bus. PCI bus, most of you are from CS background, so you have planning that it's a fast channel of communication. But when you talk about distributed memory, I talk about this computer and this computer, they are not connected by PCI bus, they are connected by wireless or LAN. So it's a slower process of connection. Here, all the CPUs are very close to the memory and connected by a physical metallic channel, and therefore the data transfer tasks are fast as well as all the processors can see the data uniformly. Disadvantage is that the main disadvantage is that's discussed already. It has a lack of scalability. You just cannot have a shared memory system with 10 processors. If you have a really large application, you cannot build a shared memory system. Why? Because you cannot find a motherboard in which you can put all the processors. Even if you think of doing that, space is an issue. The another issue is that as the processors will be very close to each other, you will generate substantial amount of heat and you need a right cooling system, which is very difficult to do. Then you need to make a schedule around the processors, which is also difficult. So there are many issues for that. You cannot just keep on increase the number of processors and make a very big parallel system. The other thing is that as you keep on increasing the CPUs, it's the same memory through PCI bus, all the processors are done. Therefore, the data transfer bandwidth, memory to register bandwidth, that is limited. As you increase the processors, only a function, typically data transfer, in terms that there are latencies and slowness in data transfer. Cache coherent systems, adding more CPUs will increase more cache memory management issues. And this is a very important thing. I'll come into it later. That see when maybe 15 years back when I was doing my PhD, we were happy if we used to get a 2.66, 2.8 gigahertz processor. That was one of the most, probably the fastest processor. Maybe very close to 3 gigahertz processor. What is a good processor now? You can think of using one for your research or some other. What should be the processor speed?
Currently it is around 1.5 with most 1.5.
4.5. 4.5 is an expensive processor. But max 4.5. So 3 to 4.5. 1.5 times increase in processor speed. But the job that I used to run during my PhD, say 1 month, this calculations are very costly, over 1,000 processors. Now, probably these people can do it in 5 days in 4 processors. So, the performance of the processors are not only 1.5 times increase, they increase by factor of 10s. How did it increase? It increased due to the issue that when you fetch data from RAM to the processor, there is a latency. But you put caches in between them to reduce the latency. The cache management have been very smart over the last 2 years. We can show you something. We can do a very back of the envelope calculation and can see that the computer speed, when you say that a 4 gigahertz processor is giving me speed of say 101 megahertz. Yes. If you back calculate and see that 1 megahertz doesn't point down to 4 gigahertz. It's not a much slower processor. So this processor speed is mainly governed by the latency between memory to processor. Now, as the cache management has been improved, this latency has come down, and that is the main reason behind much better performance of today's processors. But when you use the cache coherent system, you do not take the advantage that the memory has been very efficiently put down into the caches, because every time you say that okay, it's in my cache, but I will not use that because some other processor probably have touched down there. So these adds a very significant overhead, especially for large problems when there are a lot of cache misses, you start seeing much inferior performance. And programmer, what I told you earlier, that writing program in a shared memory system is very easy. It's a programmer-friendly platform. And you identify that this part has multiple concurrent instructions. It's possible to run this in multiple concurrent instructions. Right type of OMP parallel and combine everything. But it might not be the right one. Well, if there are cache coherence issues, if there are contentions, if there are overriding by multiple threads of the same memory space, you get wrong result or you get incorrect result. Compiler will not tell anything. Program will be compiled, program will be executed. Was this example given to you that my calculation example or summation example giving wrong result? Giving slower performance, giving wrong result. Because programming is not right. So it is possible to write wrong programs or inefficient programs in open systems. Program will run, give you either wrong result or give you slow result. So it is programmer's responsibility that you be aware where you can make mistakes, where you can do it wrongly, and you have to take care of it. So this is another important part, that programmer has to put a special effort in synchronization in order to get correct statements. Even without doing that, without missing that, he can run the program and end up in getting wrong results. Why is it very important here? Because you know that OpenMP runs over only 3 languages, right? C, Fortran. This why is only 3 languages? Why not Java? Why not Python? Or why not say, Visual Basic? Why not Julia? Because most of the scientific codes are written in these 3 languages. Now people are coming up with Python codes. But if I see that the code that ISRO used to monitor during Mars mission, during the Moon mission when Vikram will come out, this code is most likely written in C++. Or the code that some of the say Russian army is using to launch a missile, guide a missile into Kiev, that code is probably written in Fortran. Because most of the scientific community have over last 50 years written codes in C++. And these are very big codes, very big, very nasty codes. Probably nobody can pick out a single person. There is not a single person who will sit down and pick out the code and think works on the code. Somebody writes some modules on the code. Now, if somebody was in parallelizing that, he will identify his location and parallelize it. If it is done wrongly, he will not be able to find out where is the bug and finally will get a wrong result. So this is a very important aspect that you might end up in getting wrong result, but getting a result. And this will be extremely difficult to find where is the bug. So this is one of the very serious issue with OpenMP or with shared memory system when you are looking to really large problems and very complex codes. And as I said, that the processor performance degrades due to cache coherency, and basically sometimes it might happen that you go back to 10 years old performance because you are not taking the advantage of the modern processor. What is a distributed memory system? I say the next one. It also has concept. Nothing comes without this rate of number energies. If there is one energy, there will be some energy which is quality. So nothing comes without the concept. We'll see what are the concepts. There are multiple CPUs with memories. If you have a CPU and if you have a memory, it's basically a computer. So there are multiple computers which are connected via network. Processor has its local memory. The local memory space is not visible to another processor. Neither it is mapped to a global memory space during computation. So each processor is looking into its own local memory space. They are not sharing any address space. Local memory in each processor, the processors work independently. Changes in any variable of any of the processor does not readily go to the other processors. So you write something in your notebook, none of us can read that. Unless so they are connected by an interprocessor network, unless you think that you need to let us know this. And unless we are ready to listen about this. So when a processor needs to be aware of the changes in memory space of another processor, information has to be explicitly transferred from one processor to another processor. This information, this line I wrote in my notebook, I will tell it to somebody else. The other person should be okay to listen to this. You should identify what is that and to whom it should be communicated. So this module or this paradigm of parallel computing works on the basis of transferring message from one computer to another. Each computer can independently work on their area. There is no global, in that sense, global memory, global address space, global word, etc. Each one knows that this is the task given to me on this memory. I will do this task. When I think that I need to send something or I need to learn something from some other computer, this has to be done by an explicit transfer of memory. And there are possibility of through network cables you can have the total flexibility. You can transfer data among each of the computers. You need to connect them through a switch so that anybody can transfer data to anybody. That is important. Processor communication is done through network. Programmer is solely responsible for putting data transfer constructs across at desired places of program. For OpenMP, if you do not do anything, it is writing on that. There are convention, etc. But compiler will make sure that the information is written to them. Here, if you it is written in a collective manner, each processor writes. But here, if you think that this information has to be sent to another processor, compiler will not do anything unless you explicitly use a construct that hey, look into this data, send it to this particular processor. That is, inside your program, you have to write a separate construct for every processor. For example, one of the examples, if time permits, will come into it here. We are solving a Laplace equation in a large domain. We break into some small domains and ask each processor to solve the equation in its local domain. Now, in order to ensure continuity of that, you need to transfer data across the processors. That okay, you have solved something, but take his data and see whether it is same with you. Otherwise, go for another round of iteration. This data transfer, you have to write a construct that this data has to go to this processor and see if it can do this. A simple Ethernet switch can handle that, but because Ethernet switches are slower, we sometimes go to much faster networking. 100 GB or even more than 100 GB.
Suppose you break the distributed domain into subdomains, then actually we have the boundary condition along the four peripherals. Then when you divide in each rectangular domain, what will be the boundary condition that we apply at the
If time permits, we will discuss this in detail. Otherwise, we will discuss it. This is a very specific. This is a very specific example. So the idea is that there is a big puzzle. You need to put the boxes, the kids play there. Put the boxes and make map of India, and put other boxes, make maps of China, Pakistan, Sri Lanka, and put many boxes, and then you get the global. So what we were doing here, that if four kids are there, somebody is making map of China, somebody is making map of Russia, somebody is making map of Europe, somebody is making map of India, and finally they will communicate and do it together. So the local pieces, Uttarakhand, Bengal, Kerala, Tamil Nadu is given to one guy, and then the other Southeast Asia, Thailand, Myanmar to Thailand is given to another team, and they are making it separately. When they will be done, they will be done. There is idea that you have your own problem, you have your own memory, you make your part. How will you put it together? There is no global map. You will only let the other guy know that this is my boundary. See that whether you have got the same boundary, then the problem is solved. Then somebody will finally take picture and do something. The advantage is that in this level also, you have your own computers and increase the size of that. Well, so if you can, there is a network switch, multiple computers are connected, you can just bring in more computers and put it there and get a bigger size. There are two advantages associated with that. The parallelization capacity that increases because you have more processors to work. Each processor comes out with its own memory, therefore the overall memory of the system also increases. This convention to our private memory places because no two processor can access the same. So there is no cache conflict because this guy is working on its own memory, this guy is working on its own memory. There is nothing shared, nothing common. If he needs to send something, the programmer is writing an instance so that this memory is being sent to networking and computers. Therefore, the issue of cache coherency false sharing, these things are not there. You don't need to worry about the cache, which was probably your biggest storage share system. Advantages is that memory is scalable with number of processors. As number of processors is increased, memory is geometrically increased. You have two processors, 128 gram for each, you get 256 gig memory. You have 10 processors, you get 12 gig. User can rapidly access memory without graphical contention from another processor because it's accessing its own memory. This guy is working in its own memory. And modern processors capacities, what I was telling you earlier, that the performance improvement over last 10-15 years has happened solely due to improvement in the cache management that can be fully utilized. This is cheap because you do not need high-end motherboards to put 64 or 128 processors in a system. You can have in your computer lab, if they are connected via LAN, you can install some of the software and make it a flat system. Community machines can be used connected by a switch. And in RAM, in terms of RAM also, 1280 1 terabyte RAM, 1280 gig RAM. We can make it anywhere. If we insist to, we have 1 terabyte. When you go to buy 1 terabyte, it is much more expensive. The advantage is that programmer is associated for many, is responsible for many details associated with data transfer. There is 3 important details: when to transfer data, where to transfer data, and which data to be transferred. These 3 details programmer has to keep in mind and he has to write it. And if you transfer a data, see if I give you a pen, I'll be sitting idle unless you accept the pen. So if I transfer this pattern, other person has to receive it. So matching receive is also important. That is also how we receive it. Programmer has to write that processor will receive the data from the other person, and this data has to be matching also. I am giving you a whatever and you are only accepting a pen. Expecting a pen, that is not going to happen. I am giving you a big chunk of book basket, and you are thinking that I will give you Prasada. That's not going to happen. So you also have to put the right matching syntaxes so that the data that is coming and the data that is being received, that is also. Then, which is very, very complex here, and if you start writing programs, you will find out the different way you have to think on a program. That now there is no global program. The distributed memory problem is broken down and different parts are given. Everybody is solving the local problem. And finally, you have to map that. The mapping itself is very complex. We go back to the map of world. You make map of India, you make map of Bangladesh. Find how difficult it is to match these two maps. It's another problem. So it's complex in that sense. That how to map this local memory to a global data structure. And this global data structure actually doesn't end, it's a virtual data structure. You have to, it's in your clean paper. Nowhere the global data is there. Everywhere, every computer has the local data. You have required to synchronize sometime on-fly data consistency has to be checked, and finally the result has to be assigned. Important pointers for applicability of distributed. A large problem can be broken down into many subproblems with less number of operations and reduce memory requirement. This are local, particular to a node, overheads are less, conflicts and contentions are completely avoided. There is no memory contention in processors. Higher bandwidth. But the difficult part is that you now need to communicate among the processors. We are going to write programming instances for this communication. There will be very serious, very high amount of latency and bandwidth issue because data is not being transferred via mechanical channels, via PCI bus. Data is being transferred via wireless, via network router, network labs, LAN, network sensor. Data transfer is much slower. Where somewhere you think of transferring data in 100 nanoseconds, that same data will probably take some milliseconds. Transfer is much slower. Larger communication time, and therefore the communication time is much larger compared to shared memory. In shared memory, in that sense, there is no communication. Everybody is writing data to somewhere. There may be contention and coherence issues. But here there is a physical communication time. Some amount you have seen that if you think of downloading a 1 MP picture, sometimes from your WhatsApp you see that I was trying to download something, some notice came from my daughter's school, I couldn't download it. It's loading. So these things are always there. If you're working with large data transfer has its own latency. And leading supercomputers have a hybrid architecture. What is the hybrid architecture? If you have small problems, you solve it in a shared memory system. So you are getting computers which has 20 cores, 40 cores, 96 cores, I think one example was given in your 96 cores. You are getting computers with these many cores. But now if you have a big problem, then the shared memory work will be done in 96 cores. Distribute the big problem into 4 subproblems and use 496 cores. So the amount of communication is small. Most of the parallelization is done in a shared memory, but when you need to scale up, you are communicating among the processors. So it's called a hybrid architecture, where you use shared memory as well as distributed memory. You break it down to 4, 5, 10, 15, 20, 100 distributed memory system problem. Each distributed memory, each local problem is being solved by multiple processors in a shared memory.
So in case of hyperthreading, suppose the processor has two threads. So will you consider as
hyperthreading? I think this was discussed in the first class also. In HPC, we try to avoid hyperthreading due to 2 reasons. One reason is that when you only run computing programs in the front, all the HPC nodes are in the back. And you have seen our data center yesterday. These nodes, they have very rudimentary part of the OS to other programming study and only the event programming. So you utilize the entire all the clock cycles of the processors to run. Therefore, if you do hyperthreading, you are basically breaking down. You are doing one by one. But instead of using 4 clock cycles, you are using 2 clock cycles in parallel. So processor performance is coming down. Just for that. The other part is due to using 2 branches of the clock cycles, the heat dissipation is very low. And now the processors are so closely tagged. If you increase the heat dissipation, that will also be a problem. So you try to avoid it.
So one of the reasons hyperthreading may be because there is a latency from data
Right. So this is very good, very good question. And sometimes here is the latency in data transfer. There are some extent. But data transfer you do not do very often. What is important in parallel flow series question is that the data transfer will have its latency. So if we do hyperthreading, some of the clock cycles can be used. Data transfer we do not do very often. What is important in a parallel programs in order to get the performances? What is communication to computation ratio? You do a lot of computation, you do small amount of computation. So maybe after 100 iterations you go. So communication is a one-time affair, or it's less frequent affair than communication. And that's why hyperthreading is also apparent. But we do something. What we do here is known as communication computation overlap. Like the time communication is happening because of buffer to the communications to the buffers. So data is taken, data is put into the buffer, data is being transferred across the network cables from the buffers. In the meantime, processors will carry out their communication. I'll come into the communication party now. Maybe after we'll have tea and we'll finish this and then. So now another important part is that we now need to, when we think of doing distributed memory programming, now we need to be aware that we are not, our processor is not solving the global problem. Each processor is solving a local problem and it needs to think in terms of the local data structure and local problems. See, a global problem, I have an iteration 1 to 1000. Now when I go to the fifth processor, it is running say 200 to 250 iteration. But this number 200 is a global number, it is not available. The processor who is running 200 to 250 iterations is running 1 to 50 iterations. So each processor needs to, when you are writing the program, you need to think that each of the processors are only looking into the local problem and how to number the local problem, how to map the local problems from a global perspective so that we are solving them. So how can it, one of the examples is that if you do a numerical integration, there is a function and you have to find out integral of the function within it. This we have done in our class 2 that the fundamental theorem of integration is that you break the range into many intervals, evaluate the function there, and at the center of the interval, multiply with the interval width and sum them. So, if in order to get an accurate solution, the number of intervals, this number n, this should be substantially large. So, you take n 10 to the power 6, 10 to the power 7, 10 to the power 8, and you will see that the computing time increases. So, it is a good idea to parameterize this. Now, what will you do? We distribute the value into several processors. In shared memory system, each processor will calculate its local sum and then we will use a reduction. So this is a reduction operation, then they will add the local sums and get the global sum. So each one is calculating local sum. In the reduction operation, in the background there is a local variable in which, global variable in which at different location the local sums are being kept and then finally added. In a distributed memory system, this local sum I1, I2, I0 and then adding I0, I1, I2, I3, that is not possible. Why? Because each one will calculate a local variable sum. The variable name will be same in each processor because there is no other way you can define different variable for different processors. And then this variable has to be communicated to one of the processors and mapped to the names. Say I0 is retained with processor 0, ilocal is the local sum. ilocal is communicated from processor 1 to processor 0 and processor 0 receives and copies it in the location I1. Similarly, ilocal from processor 2 is communicated to processor 0, processor 0 receives it and makes it as I2. And then it will add this. And now you can also estimate that what is the communication. Communication is only one variable. Summation is done over large number of operations, large number of variables. But communication is done only for one variable. So usually we try to keep the communication. This is the data transfer part, and therefore what is different here is that each processor is basically, because you have the same program, you use a single program only, single program multiple data only. You are writing the same program, so you are using the same variable. The variable name is sum. Each processor has its own sum. Each sum may have different values. Each sum is free to have different values. Now, if one processor needs to be aware of what data is there with another processor, it has to accept the data through a data transfer process, and it has to map to the right thing. Because if it is does not mapping as some I1, I0, I2, I3, it will not be able to trace. It will be old. Matrix dot product. We can see. So what is that? That you have two matrices, two vectors A1 to A and B1 to Bn, and each of the rows and columns are respectively multiplied and added. Here are total n number of elements and NP processor which will get n by NP number of elements. Shared memory, we will see that there is a variable C which is the sum. First processor will add this part in the sum. Second processor will add the remaining part. Now you can see each processor 0 is working with A1, B1 to A and Bn. Processor 1 starts from there, AM plus 1 to A2F, B2F, the way the threads are working. And each processor, you have to be sure that there is a critical or atomic operation there when they are adding to that operation. Therefore, there is synchronization required, cache coherency required, etc. All in the same variable C which all the processors are updating. This is probably the code that using thread ID, and with the there will be overhead due to cache coherence, and it's atomic or critical. But in distributed memory, what will happen? That each process will get a local variable A1 hat and B1 hat, and each is running within the local space only, which is 1 to n. And each processor will do this operation because it's the same program which each processor is running on the same local variable space, but will load different local variables. Processor 2 will load the local variable, so it will read from the user that whatever is A plus 1 is A1 hat for processor. Whatever is A1 is A1 hat for processor 0. A plus 1 is A1 hat for processor. Each processor is reading from the local input data, global input data, but reading into the same addressed local variable space and coming up with the same solution C hat. C hats, they are communicating these C hats to one of the processor. It is taking all the C hats and sum. And here is also an equivalent reduction step. Reduction step will ensure that data is communicated from other processors and being summed up. So now you can see when you write the program, you cannot think of 1 to n. You are also in each processor you are thinking of 1 to n only. Now on what is not on your original A and B, but you have some way you have distributed this A and B to A and B heads, and each processor has its own A and B. Now, what you have to do that after all this operation, each processor is coming with a single value C hat and communicating that to the other processor. So the communication aspect is one. When we go back to the shared memory system, we can see the simulation part that whenever there is an update in C, this update is done in a critical manner. So any operation is done in the synchronized manner. But when we come here, the local summation, there is no synchronization communication, etc. When you finally communicate this C, these final output, then you need the communication. So there are very small instances in which you need communication or synchronization. Whereas in shared memory, every time you need this instance. In a matrix vector product, in a shared memory, this is actually very simple in shared memory. Different rows calculate for different processors calculate for the different rows of the product. There is no contention in writing because they are calculating for different rows, cache coherence, etc. But false sharing is possible. But if you think of a matrix vector product in a distributed memory, then different rows of the matrix has to be mapped to a local matrix, and each of the local matrix may go to each of the processors. But the vector, product vector, same product vector is copied, should be copied to all the processors because it is required by all the processors. And each one will come up with the required rows, and finally these rows will be assembled. Finally, we need to say. So there are two basic definitions we come up here. First is that here all the processors are working pretty differently. They are doing their own work at the end they are we call what is being executed by the processors is nothing but a process. Each processor is running its own process on its own memory. When we come to shared memory, each processor is not running an independent process because the same process is being run during the program. Each processor is only running a thread pointing to some parameter. So there is difference between process and thread, which is very important in parallel. Process is an executing instance of the program which uses a distinct address space. One process uses only one address space. No other in the world uses that same address space. It is different from other executing instances of the program where there are separate address space, separate resources. So the parallel computing system or processor is executing a process. When the same address space is being utilized by multiple executing instances, we call them threads. In a shared memory system, threads are being run. It was the same process. There was a basic process, thread 0, which is bifurcating, forming into multiple threads. A thread is every thread of a process share all the resources. They are sharing them. When multiple construction in concurrent instruction streams are there, who are using same memory, they are called threads. When they are not using same memory, when they are using their own memory, not sharing any memory, they are processing. A thread is a subset of the process. A process can fall into multiple threads. Threads have to be part of the process, they cannot be. Discussed about threads in shared memory system. A group of threads are launched in parallel in a shared memory system program to execute them. In distributed memory, number of independent processes are executed by the instances. A processor can launch many threads. You run a program with many threads in a single processor. But thread is specific to sharing memory. So when we talk about distributed memory system, instead of using the term processor, we use the term process. Because process means this instance is only using the same, only using its own program. When we talk about threads, they can share memory among themselves. A processor can run threads also. In a single processor system, you write a program with 8 threads running as single processor machine, it will run. It will run as group of one by one the threads will be executed. But therefore, in distributed memory system, we are mainly not concerned about threads, we are concerned about processes. Instead of the term processor, we use the term process. Earlier I said that what this processor is doing. Now onwards we will see what this process is doing. I'll leave it. Let them go in 5 minutes. Distributed memory program. There is a remote process to which message is being sent can be in the same machine or another machine. So once you transfer data, distributed memory programming model depends on data transfer. Apart from data transfer, these are completely independent processes. Each processor is running its own process. The only global sense, the only sense of final parallelization in between them comes through the fact that they can transfer data. So, a process to which one processor will send data to another processor, they can be in the same computer, they can be different ports of the same computer, then the data transfer will be done to the bus, or they can be somewhere else, anywhere which is connected, right? Distributed memory requires copying this memory. So what is this data transfer? You copy some memory from here and copy into the put it paste into the space of another processor. Copying this memory from one processor's memory space and pasting it to another by a process of send the data and the other will receive the data. Shared memory data movement was done automatically by the computer. But here data movement has to be done by the programmers, by how programmer writes the program. Programmer has to identify this data has to be moved from this processor, this data will go to this processor. Each processor is running its independent process. Therefore, within the program that is being ran by each processor, this instance must be.
So is it possible that when you are distributing task, a single task to different process goes to the process? So is it possible that we assign if a process has suppose larger capacity than other processes?
So
Is it possible that we inhomogeneously distribute a program?
So you are talking about the load balancing. So if you have a large problem, you need to distribute it among many processors. Now, one processor has better RAM, another has better Sorry guys, we got disconnected. We are again just few minutes back, so we'll start from here again. This recording is going on. I'll continue for 10 more minutes and then we'll take the tea break. Is there? You can. Audio is working also.
Yeah.
Screen not shared. Shared?
Yes.
Okay. So what we said that MPI basically works in these features. Somebody has raised a hand. If QA, if you have anything to ask, you can put in the QA, the question answer part. I can see that instead of raising hand, somebody has raised hand. Ayushi Malavia, please write in the QA part. You write your point here. You are not audible when for. Yeah. So if you have any issue, please write it here. There is a network issue, but that is resolved, right? Network issue is resolved. If you have anything to ask, you can write in the QA part. See that you monitor the QA part. So the, as I said, the idea is that there is a network cable through which there is complete flexibility. Each processor can talk to each other. It is advantage is that this is scalable, flexible. The cons programming is in general. That you have to first think in terms of a local program, and then you also need to identify which data to transfer and where to transfer its instances. Programmer has to ensure data transfer steps through communication across the processors. Is this working? Where is the presentation? This is known as point-to-point communication, where one process sends data or receives data from another process. The alternative is, which is very important, is collective communication. So instead of sending a mail to one or sending a WhatsApp message, if you put it in your website, everybody can see it. So instead of transferring data among any 2 points, if data is broadcasted to all, like when you talk among yourselves, these two people are doing one-to-one communication. When somebody is asking question to the entire class, this is a collective communication. So this feature is also collective communication. The message passing model is universal. It can fits well into separate processors connected by network. It can go to most highest level of hardware as well as workstations, laptops, etc. Anywhere you can run that, and you can connect completely heterogeneous architecture using this. People have actually connected a PlayStation with a supercomputer. And this is expressibility that this message passing model can express any parallel. Any idea on parallelization of an algorithm can be expressed like this. I told you earlier, and you can get the best performance of the modern CPUs. So we come to this MPI, the message passing is done, universally done, anywhere distributed computing, the message passing for distributed computing, for example, shared memory parallelization can be done by, you have seen OpenMP, can be done, you have also seen OneMP, can be done by OneMPI, it can be done by pthreads, it can be done by poststrings. So there are many modules for many APIs for doing shared communication. Python has its own SIMD module for doing that. But message passing is universally done by the API known as message passing interface or MPI. What is MPI? MPI is the message passing library specification. Like OpenMP, in contrast to OpenMP, OpenMP is a specific product. Many computer vendors, software vendors, research labs came together, made OpenMP forum, and decided that this API will be a computer to share communication and share validation, which is okay. There is only one OpenMP program available across the world. But MPI is a specification of it. So there are multiple different groups have created their own MPI, like an operating system, Linux. There are many versions of Linux. Similarly, there are many versions of MPI which gives you the library or many library support for doing the communication across the processors. As message passing model, it is a library that specifies the names, calling sequence, and results of subroutines to be called from Fortran and functions to be called from the C programs. That what is the input, what is the output. In the input, I will say what has to be done, which data has to be sent. In the output, I will see what is the result of the data transfer. It's not a compiler specification of a language. Programmer that use the program that users write in Fortran and C, because we are talking about OpenMP into Fortran and C, but it goes in the other languages also. These programs which you can write in Fortran and C and compile with ordinary compilers, now you can put MPI library, link it with MPI library, and run the, what is the MPI? MPI is the library functions, run the functions inside the programs. So it's basically linking your program with the library. The specific product, there are many API versions available. But API is a message passing API together with protocol and semantic specification for how its features must behave in any of the implementation. So it's a specification only. Based on the specification, different API softwares. And this is designed for ParallelComputers cluster heterogeneous. But MPI, but there is a specification. For that, there are group of forum for MPI, group of computer vendors, software writers, etc., who sat down in '93 and decided MPI primarily for CL Fortran programs. They sat down and came up with increased the features and came up with MPI 2. In 2012, they said that we'll use MPI for shared memory programming also, and MPI 3, the shared memory features. And apart from Fortran C, now MPI also is practically any language. Python, Basics, Java, Julia, any language, if two computers are working, they can communicate via MPI. The important feature is that MPI is small and exclusive. If you know only 6 MPI functions, you can parallelize any program. The best thing is that you need to know only 6 functions and you can write any program using, any parallel program using, any algorithm can be parallelized using these 6 functions. So what are these 6? MPI initialize MPI. At the end of the program, MPI finalize the MPI environment, come out of it. MPI comp size, which finds out what are the total number of processes included in the program. API comp rank, which gives the thread ID, it gives a specific ID to each process. API set and API set. It's also large and inclusive that apart from these 6 calls, there are hundreds of API functions. You do not need to remember them, but if you can find those functions and use it in your program, you will get much efficient and much less execution. can do everything with this 6 functions, but for complex program, you can use other functions also, which is also. And so maybe we'll take a break and start from here. So for the online participants, if there is any question, otherwise you write in the QA part. Otherwise we'll take a break and then start from. Do not see any question. So we'll maybe take 15 minutes break and then get back. So we'll come back after 15 minutes. For online participants, if you have any question, you can write it there, and then after coming back, I'll take it. Thank you. Audible? Now audible, right? Okay. Okay, so we'll start from where we have left. I think so. Okay. So one of the very important concepts in distributed computing, for our online friends, we are reviewing from where we have left. A very important concept for distributed computing is coming from the concept of communicator. So when there are multiple processors or multiple process now we'll say, there are multiple processes working in different processors in parallel and there is communication in between. So one process should know who are the other processes working with them because it needs to send and receive data from them. There are, say, 40 participants here. Now I give a problem and ask 10 of you to work. And you have to work in coordination with others. So you must know that with whom you will share the information. So when we get the group, when we see that these are the groups who are working, like if we go for a Goina cluster, many processes, all the compute nodes are on. All the compute nodes can go. But if we give a job to run in parallel between 32 processors, these 32 processors know that they are working on a problem which is specifically needed. So this group, that these are processors which are working independently on the respective local problems, but these processors also can communicate with others. This entire group is termed as communicator. The communicator groups all the processes who are working from there for a specific program when the program started. Say if we consider a program running with 5 processes, every process is connected with the other process and can communicate with them. Inside this communicator, the default, whenever we run any MPI program, by default, by grouping all the processes, a communicator is created called MPI call. Any communication based MPI call, sending, receiving, broadcasting, reduction, etc., must refer to that call. Must say that this is happening through this communicator. Otherwise, this is understandable also. When we run a program, the program runs in the processor. When we run a communication which involves 2 processors, who runs them? So virtually, there is a group created called communicator, and it is assumed that this communicator is running. Running this means it is ensuring through the network that the data reaches the right location, and one is sending, another is receiving. If there are 5 processes, we include the 5 processes and any possible communication link between these. This connected group is termed as a communicator. And by default, this is named as MPI mode. You can, among them, find out, say, 3 processes and create a different communicator also. We'll say that this communication will not be seen to the other rest. We create another. So it's possible to create new communicators, but by default, an universal communicator is created, which is MPI mode. The number of processes now, when you run an MPI program, With the run command, you specify your how many processes will run. Now, during execution, inside the program, like in OpenMP, we can hard code it. Now, stress is equal to 8. In MPI, there is no way to hard code how many processors or how many processors are involved. That is done during run. During execution, how can one processor identify in total how many are there? It will call an MPI call. It will use an MPI call which will return the size of the code. That is known as MPI com size. That will tell that this many processes. Each process is given in thread. It was thread ID here. It's a RAM, and this is you from thread-based calculation. You have seen that this specific ID is very important to identify which is required. So, how one process will know what is its rank? It will call another MPI function, MPI com rank, and the output will be what is its rank within the communicator. Then each process within communicator has a unique number is called. Two important questions that arise early in the parallel program is that how many processes are participating in this computation and which one among I. MPI provides functions to address that. MPI com size reports the size of the processor communicator or the number of the processors. MPI com rank reports its rank. The rank of the first process is 0, therefore the rank of the last process is size minus 1, goes from 0 to minus 1. So this now we look at your first MPI program. It's a C program. First we include the MPI header file. I should include MPI.h. Then standard C program and MPI init takes a character and a variable as by default. So you have to define and declare a character and a variable. When you write that, the MPI environment is initiated. Then you write MPI com rank, MPI world rank. So what is happening here? That once you initialize MPI, the rest of the program, or starting from there, the program is executed independently by all the processors. If you have a system with 8 processors or 4 processors, you run an MPI program giving a command MPI run minus NP executable 4. Then it will run in 4 processors. Toward top, you will see that 4 executables are running. Say your executable is hello world. You will see 4 hello world using the top. So each processor will run its own executable. While running that, then it will initialize it. Then each processor will get its current rank. Each processor will get the total number of processors. Now we'll say that hello world from process of the rank of this belonging to this size. So each process will write that hello world from process 0 of 3, hello world from process 1 of 3, hello world from process 2 of 3. MPI header file. These are the communicators. So you can see that whenever multiple processors are involved, you have to use word communicator. Communicator, you do not do anything, it is by default created. MPI word is a by default communicator. You have to utilize that. And these are the functions for library size. The compilation is MPI CC hello world.c. So Siddharth will show you in your own computer how to build MPI CC. GCC has to be linked with MPI library and you will get MPI CC and you compile that. Compiler library. And they execute similarly MPI CC in C++, MPI C++, Fortran, MPI F90, F77, etc. is a program that wraps over an existing compiler to set the necessary command line flags. When compiling code that uses Siddharth is recording of that uses MPI, and typically it adds few programs to enable the code to be compiled and linked against the MPI library with C++, Fortran, whatever is the language. MPI is supported for other languages like Java, Python, Julia, or even MachineLearning. So in Fortran, it will look like in Fortran for any MPI call there is an error variable I error, which is an integer variable passed with any MPI subject. If if MPI works fine, this error variable returns 1, else it will return something else. You can see what is inside the data. Any MPI function, this is a subroutine in Fortran, you have to call and then imply. It is similar, you will initialize MPI, the header file is MPI Fortran, MPI.h, and then find the size and rank and finalize it. The compilation is MPI 77, MPI hello. Execution command is MPI, so once you build the executable, the default executable is a. Once you build the executable, the command is MPI run -mp, then the number of processor. You have to specify the number of processor in the execution command. And what is the executable? If you run it in 8 processes, you will write hello world from process 1 of 8, hello world from process 3 of 8. So starting from 0 up to 7. And each process is running independently, so there is no order. They can write it in order. If you run it in 4 processes, 0, 1, 2, 3, but in another execution, it can be 0, 2, 3, 1. So when you write the program, nowhere you are mentioning what is the number of processors. Nowhere you are mentioning what is the number of processors. It is practically written to run infinite number of processors. Once you compile it, you will get an executable by default, that is a.out. If you simply run a.out, that will be an MPI program running in single processor. But if you have to run it in multiple processors, you have to use the execution command MPI run -np, then the number of processors. That will get the program that it has to be running this many and a.out. That means that there are 8 different a.out function executables, which are being run by 8 different processors. During their run, the processor identifies what is its rank and writes that rank. If you only run it in one, the executable, it will run in a single processor. We can check the MPI environment. So what we will do here, that during the run, MPI run, we can write that what is the MPI init, what is its return? We can write the value. What is the return of the function MPI init? Then we can say that if init is not right, if this return value is not success, MPI success is the logical field. MPI has been installed correctly and it is running correctly. Else it will abort the program. MPI abort. And otherwise it can write that what is the comp size, what is the rank, what is the name of the processor. All these things. So if we run this, we can see that first run MPI call integer, this MPI init value, return value 0. 0 means it has run correctly. MPI init will return 0. If MPI init doesn't return 0, then there is some issue with that. But we usually do not check that, just for printing out. Then it runs on the number of tasks, it runs the total number of tasks, which is size, that is 2. Rank is 1, and it is running on a computer which domain name is aliverdi.id. Successful MPI calls will always return the integer values. So this is the fundamental of MPI. Now we'll continue with how to do the communication in MPI, because that is the most significant part of it. Okay, any question from audience here or online? Any question? So there is a very I have one NPTEL course on high performance computing for scientists and engineers. I've discussed it in more detail. If some of you are interested, you can see that. So you've seen what is shared and distributed memory, how to do memory management for matrix computing, and we have introduced MPI. Okay, if participants, if you online participants, if you have any question, please write it in the QA part. Okay. So we'll see how to do communication in MPI, and we'll briefly see for some of the example cases we'll see how to define new communicators, how to create new communicators. So we'll discuss about point-to-point communication, array handling, sending an array during communication, what are the bottlenecks, blocking, non-blocking calls, collecting communication, MPI reduction, and then how to change communicator, how to create a new communicator, etc. So we have discussed this, that when we have in an MPI, we have all the flexibility that we can connect large number of processes to communication in between them. The difficulty is that programming is in general difficult. Why? We have to be aware that we are not solving the global problem in the program. Whenever we write a program, so you are writing a program to find whether a number is prime or not. You think that you take a number, check with all the possible combinations and check whether it's prime or not. But here, when you are checking whether a number is prime or not, you are probably taking a group of divisors and checking whether it's possible. And another process will take another process. So the factors will be taken differently. So that mindset has to be there from the programmer side, and the communication aspect has to be looked upon also. And another way of communication we say is, as the process have their own separate memory space, any communication between the processes is ensured by data transfer. There are two different communication models. One is point-to-point communication, where each process sends or receives data, sends data to another process or receives data from one process. This can be done in two ways. One is blocking or non-blocking. Blocking means when you send the data, unless data transfer is completed, data transfer completes means data is sent to another processor and the receiving processor has received the data. None of the processors can do anything else. All the steps will be blocked. Therefore, processors will be idle when data transfer happens. So it will add idle time for the process, latency for the process. But we do that to ensure that the process works with the right data. The solution is accurate. That is very many. The other one is non-blocking, when you know that even if the process doesn't need to use the data real time, even if the process does not have completed the data transfer, it can do some of the communication. We can use a non-blocking call. When a process is sending data to 2-3 processes, it is done usually in a synchronous manner. Once it sends data to one process, it will send data to another, it will send data to third. Once all these things are complete, we will say that the process, the data transfer is complete and the process. It can also be done in an asynchronous manner. The basic MPI call is synchronous and blocking, but we can have asynchronous calls also, that it can do it in on its own. This is basically our point-to-point data transfer call. One process is identifying which data to be sent. It is sending to the another process, and the receiving process is receiving the data and accepting it in the right configuration. The other module is communication, collective communication, where one process can send data to multiple processes. Multiple processes can send data to one process. One to many, many to one. And multiple processes can say, each process can send data to all other processes. Many people. So one idea is broadcast, that one process has information it sends to other. One process has a vector, it sends different elements of the vector to different processes. It scatters the data. Different process has different scalars. They send data to one processor, and one by one that process collects it, gathers the data, and the scalars are collected and made a vector. So there are many other type of collective communication process. So these are called collective communication. Why? If it is to be done in a one point-to-point manner, this process sending data, it receiving done, then this process will send data to it, it will receive it done, then this process send data to it, it will receive it done. So you have to write send receive for all the processes. Programmer's task would have been more complex. Here programmer's task is easy. As well as it uses the right compiler options in the background and the software interfaces in the more optimized way, so you get a better execution. If it is possible to do it in collective, you do it in the collective way. But any correct communication is possible by send receive also. This is known as reduction, that each of them have value, some value, one process collects and gets the sum. A message sent is sent or received as a packet of data. The message will have sender's address, receiver's address, data type, size and tag. So whenever we send some information to somebody, we put these things that who will get it? The receiver's address. What is inside that? If you go in a courier and try to send a package, you have to write what is inside that, and then they will find out what is the weight of that, how many quantities are there, etc. So similar things are there in the MPI send call as well as receive call. The sending message is incomplete unless it is received. So if I try to send somebody something, unless it receives that, the sending is incomplete. I cannot do anything else. Send message must match the received message as they are executed by two processes. This is very important. I write a send call, a send function. One process is sending the data. I am telling that send is incomplete unless receive has been done. But the other process has to execute the receive. So I have to write the receive instance for the receiving process also. Unless these two are done for the same message, for one particular message, it is being sent from one process and received by another process. Two different operations are being carried away by two different processes. One process is executing send, another process is executing receive. And who ensures that? Programmer has to write this in the program, that this is sent and this is received. Unless programmer writes that this will be received, the process cannot receive it. But programmer has to keep in mind that somebody else has sent it and you have to receive it. So this is very important by writing that for the same message, two different processes will execute two different operations. Every message will have from sender send destination address, the message location from where the data will be sent, the data type of the message, size of the message, and the tag. Why a tag? Because each message has to be sent, received. Now say I am sending two different letters to one person. He has to receive it. How will he receive it? By the tag he will identify what is the what will be sent first and what will be sent after that. So that tag receiver sent, there will be sender's address who is sending that, receivers will execute that. Where will it receive it? The data type and the size, they must be in combination matching. The total amount of data must be matching. And the matching tag should be there, because only after receiving the send process is complete. If the data is sent, it has to be received. Only after receive is complete, we will say that the send receive communication is complete. So status is associated with the receive. That if the status comes as success, then we will say that the data transfer has been complete. Once receive is done, then only data transfer is complete. Now, when you send the data, what do you send in our computer programs? Integers, logical variables, floats, single precision float, real variables, double precision float, complex variables, characters, etc. When you send the data, when you process the data, they are processed inside the computer hardware. So they come in terms of some electric signal, passage of electrons. When you are sending this data, this is going through heterogeneous. This is going in terms of electronic signals only, but this is going in terms of photons, packets of data. So the data that is being sent, in essence, is different from the data that is being created. The data created is something inside the computer logical gates. The data that is transmitted, that is something in the optical fibers. So, in order to demarcate between them, MPI uses a derived data type. That this data, which was integer inside the computer, when it is being sent, it is not of same size, same type. It is something some other signal. It is given a tag MPI underscore integer. That this data is called transit to the integer. So whatever you calculate as integer, when you write a send receive call, you mention the data to be MPI integer. Whatever you calculate as double precision, you write as MPI send receive instance, you mention that data in MPI terms. That is known as derived. So what is in a send command? MPI send is a function. It's all the functions have output as integer. If it is 0, then the function is executed correctly. You will see. In Fortran, it comes with an I error. So, void buffer, what is the location of the data? What is the size of the data? What is the derived data type, MPI data type for that data? Where should it go? What is the tag and the communicator? The buffer is the initial address of the send location. Count is the number of elements from there. Therefore, the data must be put in an array in a contiguous location. You have to send the initial location and the size of it. So you cannot pick data from different locations and ask them to be sent in the same single MPI call. It has to be done in the contiguous locations. You have to send the location and the size. So many times, if we have data from distinct locations which has to be sent, we create a new buffer and pack the data type, destination, tag, and communicator. The receiving protocol will be where will it receive, the location, initial address of that, what is the size of the data, what is the data type, from where it is coming, whether it has a matching tag, communicator, and status. Status says that whether the transfer is being done successfully or not. Buffer is the output is the buffer where the data will be removed and the status. And input is count, data type, source, tag, communicator. And receive are executed by different processes for the same message. You must have matching tag, data type, and data size in the same receive. Blocking call means that the process cannot perform anything unless this is being completed. This requires message to be received. In some cases, it might be started being received because it's going to the buffer. If the buffer starts receiving it, one can say that it is completed. By a matching receive call from the, so it is that send is complete once matching receive call is complete. For non-blocking, one can use MPI send data. Then the blocking issue is. So what is in a sample send receive program? There is we define a message size 256 into 10 to the power 24. For single precision variable, this amount of data will give us 1 megabyte. And there are variables x and y defined a tag 42. MPI initialized. Then we have MPI comp size and finds the size of the total number of processor is MP. MPI comp rank of the particular processor. Now we have developed this program so that I can give you an example data transfer among two processors only. Process of rank 0 and process of rank 1. 0 will send data, 1 will receive. 1 will say 0. However, inside the program, nowhere I can specify what is the number of processes. I will specify it using my execution. MPI run minus NT, number of process, and then if I run 3 processes, my job will not be completed. So what I do, I find out what is the number of processes NP, and if I see if NP is not equal to 2, then the 0th process will write that you have to exactly execute 2 processes and come out of finish the program. You cannot run it in that process. There is no other way to ensure, programmer has to ensure all these things. Nobody else, compiler or system will not ensure that you will run this process, you can run this process only processors. Programmer has to write if you are not running it to process your program. Now what do? We allocate the variable x and y to be of this size, so that 256 into 120,000, so that when you transfer their size is 1 megabyte. For I, x, we define x as what all the elements of x is 1 to 0, and y has the value, all the elements of the value, which is the rank of the process. For process 0, y is 0, for process 1, y is 1. Remember, see one thing, here we are writing that process 0 will only write that. Why? Because we do not want many statements like that. We are running number of processes. We have only one statement, you have to run it 2 processes only. So we ask only 1 process to execute. Well, now, if for the process of rank 0, it calculates what is the size, that is 1 megabyte. It says that process 0 is sending data to process 1. What it is sending? It is sending x, which is of the size, message size 1024 into 256. The variable it is x is integer, so when you send it, derived data type is MPI. Tag is, it is sending this data to process 1 with a tag is 42, and through the communicator MPI component. Once process 0 executes this, it cannot do anything else unless this data is actually received by process 1. So, if rank is not 0, rank is equal to 1, process 1 will receive this data. What will it receive? The data that has been sent in tag will receive this data. It will receive this data in the location y. That means y, which was the rank 1 earlier. Y will be overwritten by x 1 to 3. Of the same size, message size, same variable type MPI, from 0 it is receiving through MPI communicator, and then it will out give the status. Now, process 0, process 1 will send y back to process 0, and process 0 will receive y in its y location. So, process 0's y, process 1's y was 1, process 0's y was 0, process x will come and sit in process 1's y. So, process 1's y will be 1 to 3 to 5. Process 1's y will be sent back to process 0, and process 0 will receive it, and therefore process 0's y will also be 1 to 0. So once we execute, we will see this variable. We'll ask them to write x and y, and we will see what is there. Right? So printf will write what is in y0. That should be 1 to 0. This send and receiver matching, this is coming to process 1, and this send, this value is being received by process 0. Similarly, so process x is coming y, x is 1, 2, 3, 4, 5 is coming process 1's y, process 1's y is sent back to process 0's. So what we'll see, we'll write this. We can see message size is 1 megabyte. Process 0 is sending to process 1, process 0 is receiving from process 1. Y, which was 0 earlier, has now become 1. So these are 2 different operations in 2 different processes. We will be given this that tutorial session. Portrait, this send receive is done by call MPI send buf one double precision, where it will be sent what is the tag page command, and you have to put the error variable in the program. Now, if what we have done here, if we write the status comes after successful completion of the receive operation. So process 0 is sending data, process 1 is receiving. Process 0 has sent data, process 1 has received. Therefore, process 1 has executed the receive command successfully and it will have a valid status. When I am asking write status, both the processes are writing status. Process 0, what is it in writing in status? Some garbage value. Process 1 writing in its status that the 8 byte, which is an integer, is received from process 0, its rank is 1 and the tag is 0, not garbage. So from status we can identify what is being actually executed by the process. So we see the call is MPI send, the start location, count, data type, destination, tag, communicator, and the information and the error. Receive is this is the call function, the start, count, data type, source, the matching tag, communicator, status, and the error. So what happens when we send the data? First, when we start sending the data, when we operate the send command, first the sending process sends the request to send to the receiving process. It identifies in the network, in the communicated topology where the receiving process is there. Then it sends, can I send you the data? Are you there? Can I send you the data? At that time, the receiving process is not doing anything, it is sitting there. Then receiving process gets the packet. This is a small amount of data comes to the network. Can I send you the data? It's sending a signal sending the data. At that time, the sending process is sitting. After that only a send receive operation. So initially during any send receive call, apart from the data transfer time, there is a latency where data transfer is not happening, but they are only checking whether things are in the communication network and it's possible to send the data. This is known as startup time. That you need to start up the communication. This time goes. If it is good, therefore, if you have to send some amount of data, if you club all the data and send it as a single packet, instead of sending it multiple packets, you send it as a single packet. The startup time is only taken once. Only once it checks whether this is there, it's okay, and starts sending the data. However, for the data transfer part, the time will be same. There are, apart from send receive, there are other processes. Send receive is by default a blocking process, but there are non-blocking ones also. So, in the message passing based distributed memory system, we call them the cost of communication. There is a certain time taken for the communication. And these are the latency and overhead due to the interconnector or message passing, which adds to the total computing. There are three components. First one is known as the startup time. It prepares the data, makes it a packet, takes whether it is okay to send the data, takes this information, etc. So at the beginning of the data transfer, the startup time is always there. Then word time, that what is the bandwidth and how much is the data size. Based on that, what should be the actual time for transferring of the data through the network? That is it. Then another part is that, which is known as part hoc time. Because in distributed memory system, you can connect a large number of computers computers through a tree network and make a very big system. So in each of the network switch there will be some latency. As you have large number of network switches, large number of link nodes, in each link node there will be a latency. There will be some communication. So combining all these things, startup time, data movement time, and part of time. In modern network, these are usually small, but by combining all these things, this combination of all these things will give you the computation. What happens if we have a data type mismatch? See, I am sending a double precision data, that means 16 digits after the decimal place of data, and trying to receive it as a single precision data. So the data has 16 place values after the decimal. That is I am saying, but I am receiving which is only 8 places. So what will happen? I give you a big packet, you will only hold half of that, but the data transfer will not be complete. If you execute this, you can see that there is fatal error in MPI receipt, message truncated, error transfer. Data transfer is incomplete because the sending time and receiving time, sending size and receiving size is complete. If you send a float or double precision and try to receive it as an integer, the same thing will happen. Sending time and receiving time will not be the same. Because the size of the message is if I send a double precision data and try to receive it as two real precision, single precision data, two real variables, this will execute because the sizes are same. So success of data transfer depends on what is the size amount of data that has been sent and what is the amount of data that has been received. It ensures that the type of data and amount of data you have been sent, if you try to receive that, that will be received. There is no loss in data packets. MPI ensures that no data is lost during the transmission. Data loss is zero. For sending an array, we have to specify the array address and size of the array. So here what we specify, we send the variable name, we specify the address of the array and the size of the array. These are tutorials, right? Arrays, etc. Yeah, they will do these things in the tutorials. See, if you change something, what is that? There is a very important thing that if a send operation does not find a matching receive at that instance, program will not move further. There will be a problem. What is in this program? There is 1000 size array dimension 1000, which is being sent with initializing sent by rank 0. At the same instance, rank 1 is also sending that to rank 0. And they are receiving the matching receive is also there. Once you execute, it does not produce anything. Why? Because the 0 sends a data packet. Processor 1 has to receive it. Then only the send will be complete. But processor 1 sends a data packet. Both of them sending packets, nobody is receiving it. They cannot do anything else. Unless the send is complete, unless this send is complete, processor 0 cannot execute anything else. When this send will be complete, when the matching receive is complete. But processor 1 is sending data. Unless processor 1 send is complete, processor 1 cannot receive, cannot do the next step, which is receiving. When this send will be complete, when the matching receive is complete. But that plus 0 cannot do that because plus 0 is sending the data. So if you encounter a situation both the processors are trying to send in between them, nobody is receiving it, it cannot be completed and therefore program will not move any further. This is the bottleneck program. As send is a blocking call, none of the processors can receive the data. As the send is incomplete, the other receives. So nobody can. Generate the exception. No, there are ways. One of the common ways that is why that one processor you can see we have done that when process 0 sends, process 1 receives, and when process 1 sends, process 0 receives. There will be a staggering of send receive order between them. If one has send receive, another will appoint receive and send. Then this is going to stall. Program can. So we ask the odd one to receive before sending, and even before send and then receive. So what we say that process 0 will do send and receive, process 1 will do receive and send. However, this is one of the solutions. This is very well-known solution. However, the other can be done by using a non-blocking send receive if you are not worried about accuracy, or using a synchronized send receive that the processors know that they will send as well as receive from the processor. There is a call called MPI send receive. The processor already know that, and in the system level this is process 0 first sends and process 1 it receives data from process 1, sends the data packet, and it receives after the send is complete. Process 1 receives the data packet and then sends, or even the send is complete. For non-blocking calls, I send and I receive. In each of the non-blocking call, the output is request. That means the process makes a request to send. Another process will get a request to receive. Once this request is sent, that means the startup time has been taken care of, and this small amount of time. Once this request has been made, then we can say that the send process is complete. The process is non-blocking, it can take care of the request. This, if both the processes does an I send and I receive, the odd even ordering is not required, and this will work. But the issue is that if you are sending a large amount of data, unless the data has been completely sent, the process can start working on something which is probably using an older version of data, and data not actually wrong solution. I send is not blocking, processor can start receiving because before the send. So once the request to send is done, then the process can upload the data in a buffer, and the receiving processor will receive the data from the buffer, and the process can start working on it. Functions can therefore be used when the send receive is happening. That's your question. The processor still can work. They are not blocked, they can work. It can be done for overlapping communication in the if my result is computing wrong values in case of the recent data is not available for computing because data is in transit, it has not been transferred, but the process is computing using that data. There can be instead of that, one can say that I put an MPI barrier which will ask the process that it cannot do anything unless these operations are done. Then you can ensure that data transfer has been done, and then the processes can start working. MPI S send and S receive are synchronous transfer but have high overhead. Collective functions involve communication among all processes in a processor. Instead of involving communication between two specific processes, a single call handles communication between all. So whatever we can do using collective call, The same thing we can do using send receive also. I am sending data to all of you. Everybody will get a send, everybody will receive. But this is a very IoT. Once I send you and you receive it, I cannot send you. Once I send him and he receives it, I cannot send to the next person. So each send receive will have high overhead as well as wait time. Some of the processes will be sitting idle because you cannot do anything unless you receive the data. When will you receive the data? After I send the data. Everything can be optimized and a very simple function can be written if you use MPI collective function. That is MPI bcast. It will copy data from one process and send to all other processes. So I have ABCD, I use an MPI bcast. Everybody will get ABCD. Nobody has to wait for others. We reduce, which is like reduction operation. If I have ABCD, I put MPI reduce sum, then the process which is getting that 0 is the input process. It will get A plus B plus C plus. Or if I put maximum, if I put product, etc. This is very similar to reduction operation. But what happens here that local data goes from each process and follows the specified reduction operation. In MPI already reduced, all the process will get A plus B plus C plus. So whatever is done to one process, that will be done to all the processes. Very numerical algorithm, send receive can be replaced by broadcast reduce, improving, as I said, both send receive and reduce and efficiency. One of the example problem is that, say, I have number is equal to 0. For ranks is equal to 0, I get number is equal to 1. Now I say that I'm sorry. I ask the program to write what is the rank before the broadcast, what is the rank and what is the number. And for each one, number is 0 only for rank 0, number is equal to 1. Then I said that number, which is 1 for process 0, number will be broadcasted from process 0, which is the variable number size 1 MPI through the communicator. And after that, I'll ask each process to write. So each one will get 0's number, which is 1. So if I do this, and this barrier is blocking call that unless this is done, all the process will work. So that we get first the printf statement and then one printf and then get the another. So before broadcast, number is 0 except rank is equal to 1, but rank is equal to 1. So yes, but rank is equal to except rank is equal to 0. Number is 1, 0 except rank is equal to 0. Now rank is equal to 0 has number equal to 1. Rank is equal to 0, broadcast number which is of size 1 to all other processes. So every process will get number is equal to 1. This is a collective communication, but as I said, this can be replaced by many sentences, but that will increase the programming complexity as well as performance. Reduce the performance. Collective communication can be scattered and gathered, that you have a vector which can be scattered to scalars to different processes. Gathered, you have different vectors, they can be gathered as a single vector. Different scalars, they can be gathered as a vector by different. If we gather, we will say that if you gather it instead of gathering it at one processing, when we are doing this broadcast, you have to write who is doing it. Process 0 is doing the broadcast. But if I put MPI all gather, already used, etc., instead of one particular process gathering that, all the processes will gather that. Scatter V does an interesting thing. You can look into it. I'm not going into detail, but if you have a large vector, it can be scattered to define small vectors to all the processes. And MPI altogether we can take vectors of different size from different processes and combine it and get a bigger vector. These are many times done when you have to distribute a big job into many processes. You have to distribute a matrix vector product, multiplier matrix, rows of the multiplier matrix to different processes. Read it from the user and then use a gather. so that different rows goes to different processes. We do reduction. Reduction means same operation will be carried out by different process, and we need finally a mathematical sum or a logical output of that. The reduction command is that integer MPI reduce, then you put which data has to be sent for reduction, where what will be the output where it will be received, what is the size of the data, what is the data type, what is the type of operation, is it summing up, is it finding the maximum, is it product, whatever as reduction you have done in this operation. Similar operations, what is the operation associated with that, which process will get the reduction, reduced value, that is it, that is the communicator. So receipt buffer is the address of the receipt, reduction and result. The reduction operation can be for maximum, minimum, summation, product, location of maximum. Which processor was having the maximum? Location of minimum. Example, this is the forecast program. So pi is basically pi 4 of 10 inverse 1. 10 inverse 1 is pi by 4, so 4 into pi by 4. A1 is cos into cosine of the rank of the process into pi divided by the number of processors. N process. So we can see that different processes will have different values for N. Process 0 will have this to be 0, so A1 is equal to 1. Process 1 will have 1 into pi by total number of processes. So if there is 8 processes, there will be pi by 8. So you get different values. And then we try to find out what is the minimum among all the values. That we will do using all-reduce. All-reduce means all the processes will get there. What is that? That the variable is input variable is A1, which is cosine of this. Output variable, the minimum will be A. Size of that is 1. Is only one real variable, float, one float. The operation is minimization. Communicator is MPI convert and output. So we'll see that A1 has the values of 1.9 to 0.7. The minimum value is minus 0.9. After reduction, all the process one is as A, which is minus 0.9. MPI, and then we can do we can use MPI for doing matrix vector products. What is in the matrix vector product? That rows of the matrix will be multiplied with the relevant elements of rows of the matrix will be multiplied with the products relevant vector. And if you have a matrix of size n by 8, total number of operations are n square. For large matrix, the overall operation is very large. So it is one of the very common application of parallel computing is parallelize the matrix vector products. So what we do here, these are somehow learning on their own. What we do here that we take the multiplier matrix, multiply each for each row of A, we go row wise, each row of A, multiply the columns with A of that row with the B vectors, respective row elements and calculate the product. There is an interesting thing that for serial computing, single processor 1000 by 1000 takes 0.007596. If we do a 10,000 by 10,000 matrix, this is 4 9 to 8 seconds, much larger time. But if we assume matrix to be a symmetric, the ij, if I multiply the matrix by ji, it takes half of that. The same operation, but if the matrix is operated differently, what is it? Animation. If instead of ij we multiply with ji, it takes lesser amount. This is due to the fact that when a 2D variable is stored in the computer, it stores the 2D variable instead of a 2D matrix. It stores as a one-dimensional number. It is stored in C it is stored row wise, in Fortran it is stored column wise. So what is the advantage that if we really go back to our computer system, in between memory and CPU, on that I was telling that if we have a 1 gigahertz processor, ideally it would have given us 4 gigahertz. But we get much smaller because that pulling the information from memory and keeping it in register is a slow process. So usually it is one can show that if we have a 4 gigaflop speed, the performance comes down to 10 gigaflops due to this. This is big caches which are in between. There are many small memory storage locations in which data is prefetched and the way the matrix is written, so what happens that when the compiler looks for some variables, it takes some of the neighboring variables in the cache, and they can be utilized very quickly. Sorry, we got again disconnected for the online participants. Starting from here, is there anything in Q&A? Is the screen coming, Siddharth? So what I was telling that the storage is an important part, but very importantly, when we use distributed memory system, because we are storing small matrices, we avoid lot of caching. Because the matrix is small, many rows actually comes inside the machine. So we start getting better performance as we reduce the local matrices. So, and parallel performance, the way your matrix storage is there, or row access or column access is there, if you are using a cache utility version, your parallel performance will be better. So we look into a matrix vector product. The rows of the matrix will be multiplied with the vector and we get the product. So what we do here that we read the matrix from the, because a matrix is a big, is kind of a big file. We will where is that? We will, it's not here, but we'll read the matrix from the user, and then we'll send the important rows from the matrix which is at red, it will send it right 0, 0 which is red the matrix, will send some of the rows to other matrices, and other matrices will receive they will receive the matrix A with the offset from where it will be sent, and they will receive it in their respective local matrix location, and then each matrix will come up with each process will come up with the local C vector, and finally the local C vectors will be gathered, including the gather option, and the main final C vector. Another important part is that we have discussed about communicators. So whenever we have the parallel communication, send, receive, etc., this communication has been done, gather, read. Everything has mentioned about the communicator. Communicator means the group of processes which are connected. Whenever there is data transfer among the processes, the communicator is required. Now, when we run the program, when we run any MPI program, the communicator is required. There are also other features of MPI in which you can change the communicator. You can create a new communicator by grouping some. So one idea can be that if one process works as a server, which will generate some data, and others are the clients, others will take some data from the server and do some operation. So then you might require communication between the server and the clients, along with the regular communication. You belong to MPI forward. If you do a broadcast using MPI forward, then it's not only between server and workers, but master and other processes will also do that. You might not want that. So what we can do that you can make group of the processes. From there you can exclude the server and make a group with master and clients. Now, with the new communicator, you can make a new communicator there. In the new communicator, you can do a communication. There are MPI functions for them. For example, you do MPI init, find the MPI communicator, MPI component, set it as, give it a name word, and find the group, communication group from the word, which is MPI word, and name it as a word. From the word group, you exclude one of the processor and get a worker group. Take the worker group using concrete, create a new communicator of workers. And when you do communication among the workers, especially for collective communication, it excludes what is your server, rank 0. Rank 0 is excluded from. And then, if you do a data transfer, say if you once you have created that, you have created a new communicator of new com through here. Now, do a data transfer through new do a data transfer to new com that will exclude n from -1 and do communication. There is also intercommunicator processing. Sometimes and many times nowadays this is used because many problems are multi-scale, multi-physics in nature. You need to have different software taking care of different things. See, somebody is looking into breaking of a piece. There is one software which is looking into the elasticity. How the crack happens when two molecules are away from each other. The molecular energy, the bending energy exceeds molecular bonding energy like that. So in order to predict whether there is a crack in the field, you need to solve molecular dynamics. We are running another software which is looking into the force field, taking into the molecular dynamics software and checking whether the distance between the molecules are large or not. That is saying that they cannot, this is not a contiguous material, the contiguous. Now, we are running a structural, say abacus structural software. You are running Promax, which is a molecular dynamics software, and both are running in multiple processors. Only for the near-term region, there is a requirement that data will come from one software and go to another software. So you have to create two communicators because you have a single program which is giving you the final solution. You have to create two communicators. One communicator is looking into the molecular dynamics part, another communicator is looking into the abacus. And then you may need to transfer data among the communicators also. That is known as intercommunicator, where one communicator takes data and transfer to another. So these features are present in MPI, but these features are not the small among the small inclusive features of MPI, exclusive features of MPI. There are 6 functions in which you can parallelize anything. But in order to run more complex scenario, you can take many other features, and there you have to look into MPI handbooks, MPI forums, tutorials, etc., and find the relevant feature. So learning MPI is very well, of course, not in these 3 hours, but learning MPI is not also a semester long in concept because there are many features, many functions. Many times MPI board 6 or specifies a new features and includes them. You have to be updated with what MPI is doing and what are the available features. There are hundreds, more than 700 functions available. So what is that intercommunicator communicating across the processes? This is how intercommunicator happens. Okay, so we have discussed about some of the functions, and now we will have a tutorial where basically synthesis and collection, collective communication operations will be done after lunch. And you will show them one of the create program like domain decomposition, etc. If we do type publish, I give, let them do it. Like publish, I give a small introduction. Then it will give you an MPI program for a large problem, and you can test the scalability, speed up, etc. Or at least you can connect and show them the speed up. Any question?
Sir, is the last thing that you have discussed, the type of MPI is used in coupled simulation like
Coupled simulations.
So
This is not only so it's used in coupled simulation, but there are many other cases. See, MPI is the only feature for communication across the processors, and this is in different applications, even machine learning type of applications. When you have two different modules and you need to transfer data from them, you have to use intercomputers. So these are used in many cases, but in coupled simulation, this is one of the important cases.
Sir, another one is you have mentioned in which data is transferred from suppose from memory from cache to CPU. So what is the time frame if you want to communicate to the Ethernet or some cable?
You need to check so what is general network cable is 1 gigabyte per second, 1 Gbps.
Time frame is nanosecond.
So that is inside the computer. That is inside the computer through the network process. Nanosecond latency, if we come back, this Nanosecond latency is between L1 cache, which is very close to the processor, to the register. Even smaller is register. Registers in picosecond. Register is when you write A plus B is C, where A is loaded. That is even smaller. But generally in the DRAM it is around 100 nanoseconds.
Last week we have visited the pharmacy. So you were explaining like in between the cores and the rows, they use some high caliber.
120.
Yes, and to control and log in, they are using 10 Gbps.
10 Gbps is when you are communicating from outside. When in between the boxes, they are communicating about 700. But it is faster if you give a job, say 24 code job, 24 processor job, which is within the boxes, then it is actually. So it depends on what is the physical hardware for that time. That depends on it. Yes.
How the machine learning application can use this MPI?
I don't know whether there will be changes. You have a large data set to test. Right? So you need an algorithm which say you take group of the data and take some of the data. Once you come up with one training, get one set of parameters, then you think for another. Something like a sort bubble search like over sorting algorithm. There are algorithms. No, there are algorithms for that. But you can break down the data set, size of the data set. You can break down the tuning of the parameters, some of the parameters. Okay, so we will meet after lunch. Okay, for the online participant, there is a post. Is MPI intercommunication dependent on network topology? Yes. This is a very, just 1 minute. This is a very important question. So is MPI intercommunication dependent on network topology? If I go back to the slides, Revanta Kumar asked that. If I go back to the slides, we can see the 3 components of communication time. One is startup time, data transfer time, and per hop time. Per hop time is the latency at the nodes. So if you have too many link nodes in the passage, then you have higher intercommunication time. So one of the prescription in any data transfer is that go local. Try to do data transfer only with the neighboring nodes, so that the link nodes can be avoided, and make a tree-like structure so that you can go, if you have a large number of nodes you are using, always do by neighboring nodes so that you can proceed to further node using a tree-like structure. So it is important that how many nodes are there, that is important in terms of data transfer. Let me see if there is anything else. Okay. I think this answers. Thank you all, and I end the session for before lunch, and we'll meet after lunch at 2 p.m. Okay.